Hello, everybody, to this week's ISGC seminar talk. Today's speaker is Sinya Aoki. He did his PhD in 1987 at University of Tokyo. Then, after many other positions, he was from 2013 to 2025 a professor at the Yukawa Institute for Theoretical Physics at Kyoto University, and from 2017 to 2025 also its director. And currently, he is the deputy director of the Fundamental Quantum Science Program at RIKEN. Thank you very much for agreeing giving this talk. The stage is yours.
Okay, thank you for your kind introduction and the invitation to this seminars. Today I'll talk about conservation law in the curved space-time and gravity. And I think my talk is not so technical, so you can be relaxed to hear my talk. And if you have the question, please don't hesitate, interrupt me in any time. So let me explain some motivation. As you know, quantum gravity is a long-standing unsolved problem in particle physics and theoretical physics. While there are many attempts, for example, in string theory, none of them is so far satisfactory. Probably our understanding for gravity may be still insufficient. We may need to reconsider classical theory of gravity, general relativity, before challenging its quantization. In this talk, we consider following simple but fundamental questions. First question is energy conserved in general relativity? Second question is, does the gravitational field carry energy? Third question is, what is the conserved charge other than energy in general relativity? These are the subjects in my talk, and this is the content. But maybe due to the time limitation, I mainly concentrate section one, section two. So if time will be allowed, then I will consider section three and discussions. So there are some references. I started this project from 2021, 4 years ago, in the middle of COVID-19. So first, let's discuss energy conservation or non-conservation in general relativity. So we can ask why do we think energy is conserved? Of course, energy conservation is not an axiom in physics. Usually invariance and time translation lead to a conserved energy as a Noether charge. However, if a space-time is curved and time-dependent, energy may not be conserved due to lack of translational symmetry. Indeed, energy momentum tensor in the curved space-time satisfies following covariant conservation. But for the conserved energy, we need this kind of equation. Second and third term are obstruction for the energy conservation. But a natural definition of the energy, though it may not be conserved, is following. So energy is integration of some hypersurface with energy momentum tensor projected on this surface element, multiply some vector xi. Xi is the vector generating time translation. For simple coordinate system, we can write energies in this way. So in this expression, energy is nothing but the charge of time translation. So let me discuss first is the manifest energy non-conservation in general relativity. Example is the expanding universe. Let's consider the following simple metric, FLRW metric. So we have some expanding factor A, and everything is only time dependent, uniform. And for the space part, we take 3 spheres like this metric. And for the energy momentum tensor, we consider perfect fluid. T00 is minus rho, Tij is pressure, and delta J. Covariant conservation of energy momentum tensor lead to the following equation. Rho dot means time derivative. Rho dot plus 3 times rho plus P, and this A dot divided by A equal to 0. So total energy as defined before can be written in this form. And using this simple form, we get energy is rho times a to the cube times some space volume of V3, like this. It's just constant. So if we take time derivative of this energy, we get rho dot plus 3 times h times rho. And using conservation of energy momentum tensor, we can rewrite this is this term is right-hand side like this. Therefore, if pressure is non-zero, time derivative of energy is non-zero. That means energy is not constant. It's not conserved. So this means energy decrease or increase since the space-time expand against positive pressure or negative pressure. That means matter perform positive or negative work to the space-time piston. Or this manifest example of the energy. This is the manifest example of the energy non-conservation in general relativity. But see later discussion. Although we have the example of the energy non-conservation, let's first discuss situation. The energy is conserved in curved spacetime. First example is very trivial one, conservation by symmetry. So if the vector xi mu for the time translation becomes the killing vector, which satisfies this equation, then vector which constructed from energy momentum tensor and this vector is covariantly conserved, like this. Because T mu is conserved, this only act for disk Z, but T mu is symmetric, we can write in this form. And if Z is a killing vector, it is conserved. And if the metric G mu is independent of the time coordinate x0, this vector becomes the killing vector. This is well known. Of course, in this case, time translation becomes symmetry because metric does not depend on time. This simple definition of energy first appeared in the textbook by Fock, 1959, long time ago. However, this definition is almost overlooked in the major textbook or literature, except a few. And we can use this definition to calculate energy of the compact star. So we consider some compact star, and if we saw this star from far from outside the star, then we can get just a Schwarzschild metric. The metric is given by F and H, and inside the star, F and H is not does not satisfy this relation. And inside the star, we have the perfect fluid like this. But outside the star, we see the Schwarzschild metric. F and H gives the Schwarzschild metric like this. This MR is the so-called Misner-Sharp mass at the surface, radius R. And the Einstein equation for this situation becomes T of equation, as you know well. And the formula for Misner-Sharp mass at the surface can be written in this form. It's 4 pi times R integral from 0 to R, R square rho R. Rho R is the T00 component. But of course, this is not covariant. And the total energy, on the other hand, from our definition, we get H has this form. Because of square root of G, we have F times A in addition to R squared. This form is covariant. And we can rewrite this total energy equal Misner-Sharp mass plus some correction. This correction is due to the internal structure of the star. We write this is delta E. In the Newtonian limit, this delta E can be written this form. MR is replaced large R to small r, so Misner-Sharp mass at radius R times rho R and integration over R times dr. On the other hand, if we consider Newtonian gravitational potential energy, which mass at x, mass at y, and with Newtonian potential and the integration over x and y, we get this form. Therefore, this correction term in the Newtonian limit is equal to Newtonian gravitational potential energy, which must be negative. Therefore, total energy E, mr plus delta is smaller than mismatch mass mr. That means the total energy is different from gravitational mass seen far from the star. And we can calculate this correction term, size of the correction term. For the constant density, rho r is constant, the maximum of this correction term is 68% of mismatch mass. Therefore, extreme case, the total energy of the neutron star is much smaller than the observed mass. If observed mass is 2 solar mass, but total energy is 1/3 of this mismatch mass. The second example is conservation without symmetry. If the time translation vector xi is not Killing vector, but satisfies the following condition: T mu nu times del mu xi mu, and since xi is a constant vector, so it's just T mu nu times gamma mu nu, the Christoffel symbol. And this, of course, after summation over mu and nu, and this quantity becomes 0, J mu is covariantly conserved because of this equation. In this case, energy is again conserved. The example for this case is some type of gravitational collapse. So let me consider black hole made of the normal matter, which has been proposed by George Obar in this paper. He replaced Schwarzschild metric in time-dependent mass mr, like this. The simplest mass function is given here. So inside star, this has r cube, r to the 4th. But outside star, it's just constant. It's Schwarzschild metric. So h is the horizon side. And this mr is written in red symbol. And each term has different behavior like this. And property of this type of black hole is the following. There is no inner horizon, unlike regular, so-called regular black holes. And also energy momentum tensor satisfy some kind of energy condition, like null, weak, strong. So it's these two indicate this is physically non-exotic matter. And singularity is, this black hole has singularity, but this singularity is less than Schwarzschild one. Because if calculate Kretschmann scalar, it's 1 over r to the 4th. For Schwarzschild black hole, 1 over r to the 6th. And also, Rich scalar is integrable. Rich scalar is 1 over r squared. Therefore, we can integrate over the major term cancel this r squared. And I'd like to consider collapse of this type black hole to the Schwarzschild black hole like this. For this purpose, I introduce so-called Eddington-Finkelstein coordinate from T to T bar using this change of variable. U is minus 1 over 2 mr divided by r. And we can get this metric. And here we drop bar. So this T bar now I write T. And in this coordinate, T constant hypersurface are space-like. So T constant one is written in red. And this constant hypersurface always space-like. Therefore, we can consider T as a time in this coordinate system. Although singularity itself is also space-like, attached to the end of this space-like time surface. And mass function is written here, and we introduce time dependence as like this, mr. So instead of mr, we write mrt, and x now become time dependent. Xt r divided by h times e minus WT. And this metric only used for xt is smaller than 1. Therefore, if t becomes larger and larger, range where we can use this formula becomes smaller and smaller. So this figure is like this. So first, t equals 0, we have the horizon and matter inside. So metric is deviate from Schwarzschild metric. But if time increase, vacuum region inside the horizon develop during the collapse. And now for the blue curve, up to here it's vacuum. Horizon is still here, but vacuum and some matter. And vacuum region is larger and larger, and finally become Schwarzschild black hole. This is proposed by me and Aubert this year. And we can calculate energy momentum tensor during the collapse. This energy momentum tensor is classified so-called Hawking-Ellis type 2. We have T00, T11. Prime is R derivative, dot is time derivative. And we have 0,1 and 1,0 component, which is matter moving, and T22 and T33 is equal, like this. And one can explicitly check the condition. This is equal to 0 from this energy momentum tensor and met the Christoffel symbol. And we can calculate total energy for this. So we consider T mu 0 and this hypersurface, and we take this metric R squared and T00. And our metric, this U term is cancelled, only appear in this R square in the determinant, like here. And the T00 is R derivative of M, and R square cancelled by this R square. And this is just total derivative. So we get M at infinity and 0. M0 is 0 because the function has this form. So R equals 0 becomes 0. And M infinity is it's just mass M. Therefore, we get M divided by G Newton. The total energy E is conserved and agree with the black hole mass M. And let's discuss similarity of this. And during the collapse in finite time t, no Schwarzschild singularity at R equals 0 develop. If we calculate Kretschmann scalar R square like this, and in the matter region, it's 1 over R to the 4th like this. And the vacuum region, it's R to the 6th. But this is outside this condition. Therefore, in R to the 0, it's always R to the 4th. And during this collapse, we can discuss energy condition for energy momentum tensor according to these people. And we have time dependence T, and we consider this omega is proportional to the horizon side. So we consider alpha, and the null and strong energy condition are satisfied if collapse is sufficiently slow. So R is smaller than this number. And also weak energy condition is satisfied if alpha is smaller than 1. Therefore, matter describe this collapse is physically acceptable since they satisfy energy condition. So let's discuss final state of the collapse. So this mass function becomes T go to infinity limit becomes Schwarzschild metric constant M except R equals 0. R equals 0 is always 0. Therefore, we need theta function. Theta 0 equals 0. So limit is Schwarzschild vacuum except R equals 0. We call this is a regularized Schwarzschild metric as a distribution. Theta function is a distribution. And using this metric, we can get non-zero energy momentum tensor at our origin, which has been calculated by our shown in our paper. And we get T00, T11 is some coefficient some quotient times delta function divided by R square. T22 and T33 is delta function derivative divided by R. And you can see this metric, this energy momentum tensor is not perfect fluid. It's non-perfect fluid energy momentum tensor, which is different from Oppenheimer-Schneider gravitational collapse, which pair, they use perfect fluid energy momentum tensor. And also this energy momentum tensor agree with the energy momentum tensor in the distributional approach by these people. And we can calculate black hole energy using this energy momentum tensor in our definition of T00 and integrate over volume. We get, because of delta function, we get non-zero value like this. That means the Schwarzschild black hole is made of the point-like matter at the origin. And its energy can be calculated from its energy momentum tensor using our definition of the energy. So the mass function MRT describes the physical process of the gravitational collapse leading to the Schwarzschild black hole realized by theta function at the origin, like this. So now I would like to go to section 2, but some question so far? Okay, so I'll go to the section 2. So does gravitational field carry energy or not?
Sorry, may I ask a question?
Yes, of course.
Does the theta term at the zero radius, does it mean a delta function? Does it resemble a
derivative becomes delta function. Yeah, because of this MR, and we calculate using this, we calculate T00, T11, and usually if we consider constant, it's just 0. But because of theta, we get delta function like this or delta function like this. Derivative of delta function like that.
Yeah, but for the case of the Schwarzschild, we have a singularity at the origin, so we cannot find a delta. Can we find such a delta function for the usual Schwarzschild or not?
No. Usual Schwarzschild, since theta r equal, it's 0. So 0 divided r is 0. Right? Of course, it's not continuous function, but because it's distribution.
I mean by the singularity at the origin of the Schwarzschild, we cannot find a delta function for these T00 or at the origin. No, we cannot.
Sorry,
I mean for the standard Schwarzschild, we have some divergences at the origin. So I could imagine that the T00 could be like a Dirac delta function, not totally. Yeah, so could they be similar or they are different in this respect, this solution?
Yeah, it's same. Actually, these people calculated the Schwarzschild T00, so they get same answer like this.
Okay, so they are the same.
Okay, same. Yes, yeah.
Thanks.
So yeah, they use the different regularization, but it's in principle it's same. Okay, thank you for the question.
Can I follow up with one question?
Yeah.
It's just on what you just said. In the usual Schwarzschild case, I'm actually familiar with that last result, delta prime of R over R, right? But in the usual Schwarzschild case, the interpretation I would think is quite kind of exotic because R is time inside the horizon. Isn't that right? In the usual...
Oh, no. It's really tricky because of this metric. It's not usual coordinate. It's Eddington-Finkelstein. So T equals 0 is like this.
For your case, but what I'm saying is that for that reference that you're citing, the 1993 and what was the other one? Those guys who calculated that delta prime result, the one
it's using standard standard metric. Yeah.
Yeah. So
Yeah.
I'm asking because then the comparison is a little bit tricky, no? Because in the usual short approach, R is time. But I understand on your side, you're advocating R to be. I mean, your T is still time.
Actually, sorry, these guys using a little bit different notations. They don't use in terms of R, but they use some different coordinate expression. But result is the same in our coordinate and their coordinate. If you match the coordinate system, it's same.
But the interpretation is a little
but yes. I forget detail, but they don't use R. They use some different notation. Sorry.
Okay.
Thank you for the question. Okay, now go to the second one. So, because the energy is not conserved without considering gravitational field, we'd like to consider energy of the gravitational field. So, like external electromagnetic field, one may think to define energy for time-dependent dynamic gravitational field, which recovers the total energy conservation. Indeed, since time translation is a part of a general coordinate transformation of general relativity, this is the local symmetry, one may define the conserved energy using this symmetry. However, so-called Noether's second theorem invalidates such a naive thought. One cannot define the conserved energy covariantly. So as mentioned before, the energy momentum tensor satisfies the covariant conservation as is, but this is obstruction. And usually in a textbook or historically, the people define energy in the following ways. Old one is traditional one, so-called Einstein's pseudo tensor. People give up the covariance, and they consider standard energy momentum tensor plus small t mu nu and satisfy conservation law. This small t mu nu is called so-called pseudo tensor. Pseudo tensor means this is not covariant under the general coordinate transformation. And Einstein interpreted this is a gravitational energy, and total energy is calculated from this. But in a modern textbook, people using so-called quasi-local energy, people in some sense give up a local definition of energy or energy density. This type is so-called Komma or Bond, ADM or Gibbons-Hawking, etc. So instead of energy is calculating energy from local density, volume integral of the local density, people calculate or define the energy as the surface integrals of some so-called quasi-local energy like this. And before discussing these two, let me introduce so-called Noether's second theorem. And before that, first consider Noether's first theorem. So we have the action S, which depends on field phi and its derivative. Maybe it's second derivative, etc. But for simplicity, we consider first derivative. The equation of motion by the variation of the action gives usually this way, and by the integration by part, we get this equation up to surface term. And because M is arbitrary, we can get equation of motion like this. Now consider the global symmetry like this. So we have some constant parameter theta 0 and some variation of the field delta G. And the symmetry says 0 times theta and the phi and del phi. But using equation motion in this part, you can replace its derivative of these guys. Therefore, this part becomes total divergence. And the M is arbitrary. We can get this quantity must be conserved, del mu and mu equal to 0. And this N mu is so-called Noether current, defined in this way. And the important thing is for the conservation of the Noether current, we have to use energy momentum as equation of motion. that means conservation is dynamical. So it reflects the dynamical property of the system. Now let's consider Noether's second theorem. We consider local or gauge symmetry, and the field is transformed by some time coordinate dependent parameter 6, theta, times some function phi, and which contain derivative which act on theta or something. And under this variation, without using equation motion, we can always write in this form. So first term is theta without derivative times some x. And also we have total divergence. And this is always possible because if we have some derivative acting on theta, we can always remove this theta times some total derivative. We can always do that. Of course, it's very complicated, but we can always do that. And since theta is local parameter, we can take theta x equal to 0. That means variation is 0 on the boundary of the system. Since because total divergence, contribution becomes only, exists only boundary. Therefore, second term is does not contribute to this equation. That concludes x must be 0 for without using equation motion. And since without this term, the 0 must be equal to this for arbitrary theta x. Therefore, we can take theta x, which non-zero on the boundary for arbitrary n. That means this inside must be 0, del mu j mu equal to 0. Again, without using equation motion. That means this conservation is always satisfied, and therefore it's not dynamical, non-dynamical, or just constrained in the system, like Bianchi identity. So this conservation does not reflect the dynamics or equation motion of the system. That is the problem of the local gauge symmetry. And if we apply this argument into the general relativity, we can obtain following result. So let's consider the local translation. So general relativity symmetry is written in xi mu x. This is coordinate infinitesimal coordinate transformation. If we consider Einstein action plus some matters, we can get following current J mu xi, which can be written xi with del mu is anti-symmetrized and derivative with covariant derivative between mu like this. And we can also expand this in terms of xi and its derivative like this. Of course, it's a simple derivative. It's not covariant, of course. And interesting thing is there is no matter contribution. We can always write a quantity like this. And because of this anti-symmetry, this current is, this is actually current density because of this is always conserved by this form. And the conservation of this current implies also conservation of this first term like this. And we have chain of the identity using, since xi is arbitrary. And actually this current mu nu can be written again, derivative of the anti-symmetric quantity like this. We here emphasize again, this hold for an arbitrary metric g mu nu without using equation motion and arbitrary vector xi. And let me show some mathematical structure of this non-dynamical conservation. So we consider current from second theorem is j mu xi, and which corresponding one form like j, like this, j mu dx mu. Covariant conservation means the Hodge dual j equal to 0. This is exterior derivative. And non-dynamic conservation means j can be expressed as db star. B is 2 form, so D is 3 form, but star is makes this j is 1 form. Then conservation is trivial because the d star j is equal to d star square dB, and star square, for this square is -1 in this case, and the exterior derivative d square is trivially 0. So its trivial conservation means d square equal to 0 in this case. And also integration over space-time for this dj becomes using Gauss theorem, it's become boundary integral of star j. But if j is star dB, we can write this as dB, and using Stokes theorem, it's b over boundary of boundary. And the boundary of boundary is always 0, so this is trivially again 0. And this problem is pointed out by Noether in 1918, and we can find this paper in archive like this. So she says the failure of law of conservation of energy proper with general relativity, or the failure of proper law of conservation of energy is a characteristic feature of the general theory of relativity. And now, from the point of view of the Noether's second theorem, let's discuss the standard textbook definition. First, let's consider pseudo-tensors. In this case, we just take GZ as global time translation. And so we consider J mu is A mu 0 like this. A mu is given here. Of course, this quantity is conserved, but we can rewrite this quantity using equation motion. So R mu nu, blah, blah, blah. So what we can get is T mu 0 and small t mu. T mu nu is defined in this way. And Einstein, the interpretation in this energy momentum tensor, this is energy momentum tensor for gravitational field. And total energy can be written in this way, but we always have quasi-local expression using this form. And also quasi-local energy is similar. So we can define off-shell but covariantly conserved current density using vector GZ mu like this. And we can have quasi-local charge like this. And we always rewrite it in terms of quasi-local surface integral. One can construct infinitely many conserved charge depending on your choice of disk Z. For example, coma energy or bond energy, ADM mass, or sometimes Bold entropy or asymmetric charge, etc. So let me discuss some problem about energy from the second term. First of all, as I already mentioned, the conservation is not dynamical, just constrained. And physical meaning of energy is unclear. The conserved energy may not be conserved as the conservation is non-dynamical. So usually conservation case is if contribution on that boundary current d xi mu j mu equals 0, then integral of this and integral of that is equal. However, usually in the this Noether's current from Noether's second theorem, since there is no physical reason, it's not difficult to say this is always such. As I said before, the conservation coming from some trivial cancellation. Therefore, it's not necessary to say this is this contribution is 0. So we have to check always this. And conserved charge can be defined separately for each invariant term. For example, if we consider Einstein-Hilbert action, we consider matter action, for individual term is invariant under general coordinate transform. Therefore, there is some the conserved charge corresponding to each term. In this case, no exchange of the charge between gravitational field and for example, matter doesn't exist. And also we can freely add total divergence to change its definition and the numerical value. Together with the choice of GZ, arbitrariness of GZ mu, there are many definitions of the energy. The question is which is the correct division of the energy. And also, one may discuss, we may just employ Noether's first theorem for the constant time translation by ignoring the second theorem. However, for example, for the simple model, we obtain Noether current from the first theorem and Noether current from the second theorem, and we consider difference. A difference is proportional to equation motion. Therefore, if we employ the equation motion, current for the first theorem is equal to current for the second theorem. That means current from the first theorem is also constrained up to the equation motion. So some brief summary on part 1 and 2. As evident from the previous example for the expanding universe, the energy is not generally conserved in general relativity. Energy from the pseudo tensor and quasi-local energy both vanish in this example, since there exists no boundary and we cannot define quasi-local energy in this example. The energy from the second theorem is not physical energy because it's zero in this example. It seems difficult to define energy for gravitational field or space-time itself. However, one can define energy for the matter, which is covariant and local, but may not be conserved by this expression. And Z is a vector for the global time term. Then there is a question. So since energy is not conserved, following process might be occur. That means vacuum creates star or black hole. So if we have the vacuum, that vacuum means T mu equals 0 or G mu equals 0, but we have some Riemann tensor, but no singularity at this point. Then using Einstein equation and covariant conservation, and maybe we require some positive energy condition, but not energy conservation. And that vacuum can become non-zero energy momentum tensor, which means star or sometimes singularity like black hole. But in the remaining 15 minutes, we'll argue this is unlikely to happen. And that using some universal conserved charge in general relativity. So some question in this part?
You did not mention the equivalence principle. Am I right?
Yeah.
I'm just wondering because I think one of the at least that's how I always understand it, that it's not possible to define local energy for the gravitational field because you can always make its first derivatives vanish at a given point, right? And that in turn is, I thought, intimately related to the equivalence principle.
Yeah, okay, yeah, I understand your point. But that is strongly influenced by pseudo-tensor argument. Since pseudo-tensor is not covariant, you can make locally it's zero. But if you define something in covariant, you cannot make it zero. So that means you assume energy for gravitational field is non-covariant, right? So that argument is if energy of gravitational field is non-covariant, you can make it zero. But if although we don't know, if we can define it covariantly, you can make it vanish.
And I was also just wondering whether it can be a guide. I don't know whether it's a hindrance or guide, but is it possible to be a guide for what should the correct answer be?
Correct answer for
the energy momentum.
So my conclusion is we can only define energy for matter, not gravitational field.
I see.
That is in covariant sense, in a covariant sense. That is my conclusion. And clear example is expanding universe. No way to.
Yeah. Sorry. I have a related, but
yeah, I know.
you may be. I'm sure probably you are aware that There is this in particle physics. There is this theorem. I don't know whether to call it a theorem, but basically you can kind of bootstrap your way and start from the linearized version of GR and kind of build your way non-linear complete GR using its gauge symmetry. And for example, I think Dazer, right? Stanley Dazer had this construction where I think you use the kind of Palatini action. You can just iterate it one time.
Okay.
And you can get the full GR action, right?
Yeah.
So I wonder, is that also a guide to, because I think that part is slightly related to the Noether theorems that you're talking about.
Yeah, but I think they use Hamiltonian system, and if I understand correctly, they introduce some coordinate, then discuss energy. But honestly speaking, I'm not so. I cannot clear connection between Noether's second theorem and their argument. Maybe let's discuss later in some point.
Okay. Yeah,
that's an interesting point.
Yeah, thank you.
Okay, so let's consider conserved charging curve spacetime, including GR. And this is some references. So we start with some energy momentum tensor. We consider the energy momentum tensor in the following form. T mu is energy density time mu nu u mu u nu u mu is a time-like unit vector, and also pressure tensor. Pressure tensor is orthogonal to this vector. So this energy momentum tensor, which is classified as a Hawking Ellis type 1, covers standard classical matter in 3+1 dimension. This is famous textbook, and also we assume is satisfied. Conservation is satisfied. And to set up the argument, we first pick up an initial space-like hypersurface, HT-1, like this, and introduce coordinate y1 on this hypersurface. So this hypersurface is defined hx mu as a function of y is some d-1 parameter. And we pick up any point on this surface and consider the curve starting from this point using this differential equation. So dx mu tau y, d tau is equal to this vector u, which is introduced this energy momentum tensor, defined energy momentum tensor. And the initial condition tau equals 0, we start this point p, like x mu p. And for all points on this hypersurface, and we have the foliation of the hypersurface hd-1 tau. So hd-1 tau is h mu tau y, and y is on this surface, and tau is some foliation parameter. And by definition, tau equals 0 becomes original hypersurface. Using this setup, we consider this is hypersurface. Hypersurface, we have vector u, which becomes a curve of define the correlation. So it's time-like vector from energy momentum tensor. And we have also a normal vector on this hyper. Usually, in general, normal vector and this vector is different. So we have normal vector. And we also have tangent vector, the vector parallel to this hypersurface. So this is usually write E mu A. So we have d-1 vector in the tangent space. And the HAB is induced metric on this hypersurface, and H is determinant of this HAB. So we then calculate covariant divergence of this vector, like del mu u mu, which I write K. And after some calculation, this K can be written inner product of this vector n and u, and determinant of this H, and derivative of this time variation like this. And I skipped the derivation, and if you are interested, please look at this difference. Then our proposal of the conserved current. So we construct conserved current from energy momentum tensor using this vector u and the scalar function theta. So J mu is T mu nu times this vector times scalar. And this vector, so this combination we call theta nu. And by definition, if we multiply u nu, it gives minus, and this becomes 0. Therefore, we have epsilon theta x u mu like this. And this division is coordinate independent because we use vector from the energy momentum tensor. And for the spherical symmetric case, this vector, which makes J mu is conserved, is known as the Kodama vector, which was proposed 80s. So we determine this scalar function in order to satisfy the conservation law like this. So we consider covariant derivative of this J mu. And this combination is scalar, so we just standard derivative times this vector. And this derivative also acts on this vector. But this part, from this division, it's nothing but half derivative of theta epsilon. And this part become k from our definition, previous definition, like this. Therefore, and this must be 0 because of the conservation. Then we can easily obtain this combination is equal to tau equals 0 and integrating over this quantity from 0 to tau. Since this k has expression like this, it's tau derivative. We can easily integrate this, and we get this. Since this is log, we get ratio of this at time 0 and time tau. Therefore, the conserved current is determined as current is equal to initial value of this function theta and initial energy density and the initial normal vector 0y and u and squared h, and also this tau dependent like this. And we have some free parameter at initial condition like this. And we discuss initial condition and some physical interpretation. And if we apply our proposal to a system of particles interacting with each other only by gravity, we obtain conserved current J mu is some mass term and some this initial condition theta n. And this is vector velocity of the particle, and x is particle world line, and tau is proper time. And we have this expression. And in this case, we can easily calculate conserved charge. Conserved charge is nothing but this m times theta n. This is the initial condition from n1 to n. Therefore, simple initial condition is this theta n times m, n equal 1 for all n. That means charge is nothing but particle number. In the general case, this initial condition corresponding to theta 0y times energy density 0y is equal to 1 at time tau. Then we can get charge is in this expression. So tau dependencies disappear because in an integration, this part and this part is canceled out. So we call it, so since there is no information of energy density, we call it geometric conserved charge. But initial different in the condition is considered. We can consider theta is just 1 for all. That means Q is equal to total mass. And general case, if we take this initial vector is 1 for all y, what we can get is this expression. Again, this expression is how independent and it's conserved. It might be interpreted as total gravitational mass or gravitational charge. And this is total gravitational charge or mass. This conserved charge is different from non-conserved energy. Energy is defined in this way. In this case, we have different expression like this. So very different from conserved charge. And existence of the conserved current looks trivial since it's particle number or total mass. However, it is non-trivial. Such a trivial conserved current can be constructed from energy momentum tensor in a covariant way, which is, of course, energy momentum tensor is physical and made of various matters. And also, interestingly, in the case of the perfect fluid, this charge corresponding to entropy and Gzi corresponding to inverse temperature. So that means this epsilon times theta is nothing but entropy density for that in the case of perfect. And this can be written the ratio of this quantity, n times u times square root h tau over there. And if we consider radiation, so without conserved particle number, we obtain energy density equal to something times t to the fourth. This is nothing but Stefan Boltzmann law. So, and also we can determine the local temperature, which proportional to time dependence can be controlled by this quantity. So if you are interested, please look at these papers. So let me conclude. So we can define matter energy, which is not conserved in general. And there is conserved current in this form. In the case of perfect fluid, there is an entropy current, while the theta is an inverse temperature. And because of the existence of such charge, such current, transition from vacuum to matter seems impossible. Because of the vacuum case, since there is no energy momentum tensor, this J mu is always 0. That means two gravitational wave cannot create star or singularity. However, if some energy conditions are violated, a creation matter or singularity from a vacuum or its inverse process become possible. For example, in this paper, I discuss colliding two gravitational plane wave like this. Gravitational wave coming from here. This is Minkowski, this is plane wave, and it's collapsed. This is nothing but an annihilating universe, and we have the singularity in this line. And in this singularity, there is an energy, and this energy is not conserved and becomes 0 at this point, but charge, these charges conserved, and always charge is always 0. But in this situation, null or weak or strong and dominant energy condition is violated. Therefore, if we violate such a condition, we can easily create singularity from vacuum or vice versa. And for the quantum gravity, and first is a physical meaning of this conserved current for a generic EMT. And in the current discussion is only using energy momentum tensor for Hawking Ellis type 2, but type 1. But for generic EMT, may give a hint for quantum gravity. And the quantum gravity must satisfy gravitational field classically have no contribution to J mu. Therefore, they have no exchange of this gravitational quanta with matter in the classical limit. The question is, should gravitational field be quantized? Thank you for your attention.
Thank you very much, Sinya, for the really nice talk. Are there any questions?
Do you mind
please.
going back one slide? I'm just curious, is this related to, or has this any relation to the, what is that called? Hooke. Is it called the Hooke conjecture? I don't know what the status of that conjecture is, but basically I think if you squeeze enough mass in some region of space-time, you would get a black hole, something of that along those lines. So I'm wondering if is that something like that happening here?
Sorry, I can, which theorem?
I think it's
Conjecture?
called the Hooke. I'm not. It's been a while since I looked it up, but I think it's called the Hooke conjecture. So if you can like move, I can't phrase it in a short way, but basically, if you squeeze enough stuff inside a given volume in space-time, then I think the conjecture is that there will be a black hole.
Okay, that's interesting. So from even in vacuum.
This is due to Kip Thorne, I believe. And I believe some years ago I even saw the angular momentum analog of that. But so I am wondering whether, because since we're talking about energy of the gravitational field, right? So so I guess maybe one question is it possible to generate such strongly self-gravitating gravitational waves, highly nonlinear, enough that you can form a black hole out of it?
Yeah, that's this example. For example, if it's turned around, that means from nothing, universe is created, and the energy is increasing. And this singularity is not black hole, but something similar to black hole. That process is possible, but however, problem is in this case, the energy condition is violated. So maybe problem is that process could be possible, but one has to check energy condition. If you violate energy condition, anything could be seems possible. That is my current understanding.
My rough understanding of the Hooke conjecture is that it does not require exotic energy conditions.
You don't need. Okay,
I don't think so. I mean, maybe somebody else in the audience.
Maybe okay. I will. Maybe if please let me know. I'm not so familiar with it.
Sure. And
of course, there is some numerical simulation, and they observe some singularity, but from vacuum.
I think I've heard numerical relativists talk about the Hooke conjecture as well. Because you can test it numerically, right? I don't know what the status of the theorem itself is. Sorry, I mean conjecture. I don't know whether it's a theorem yet, but my understanding is that even numerical relativists have tested it on the computer. And but my understanding is that it holds in the scenario that they have tested.
Problem is the numerical relativity. People only consider the up to horizon, so they cannot go inside horizon. So they don't know what is inside the horizon. It's matter or vacuum or matter satisfy energy condition or not.
They cut it out, right? You're saying that
yes.
They
usually
cut it out. This I understand. And this is classical, right? Your statement that
of course, everything is classical. Everything is classical.
Because I would think that or maybe do you think there's something like the Schwinger effect in GR? Like, if you turn on a strong enough gravitational field, then in principle you can get kind of spontaneous production of stuff.
But Schwinger effect, you need plus minus charge, right? That means we need plus minus energy. Otherwise, we cannot create from zero to non-zero.
I see.
Of course, it's right. The electric field doesn't have charge, but because it's strong enough, quantum have to create electron and positron pair. But charge is conserved. But energy case is different. We don't have negative energy. Or if we have the negative energy, such a process is possible, but clearly violate energy condition.
I see. Thank you.
Thank you for your nice, interesting.
Can I ask you a question regarding the definition of the covariant
Yeah.
current?
Yeah.
Yeah, what is the motivation to introduce this scalar function epsilon?
Yeah, because
Yeah.
so for the conservation, we need some not tensor vector quantity like J mu. So we need using energy momentum tensor, we need some vector. So natural choice is vector coming from energy momentum tensor. However, problem is this without theta, it's not conserved in general. Sometimes conserved, but it's not generally conserved. So we actually introduced this scalar function in order to satisfy conservation law like this. And but from this conservation law, we can determine behavior of the theta. So it looks rather ad hoc. But for example, the Kodama vector corresponding to this combination for some spherically symmetric time-dependent case. And also interesting things is this theta sometimes become inverse temperature. For example, expanding universe, it's corresponding to inverse temperature. So expanding universe for the perfect fluid, entropy is conserved, although energy is not conserved.
And my second question was like, you only considered type 1.
Type 1, yes, yeah.
What does prevent you from using type 2? Is it?
Yeah, maybe for type 2 case, we have T mu has null specified null vector, 2 null vector and some the space-like vector. But there are 2 null vectors, so I'm wondering how to define. Maybe we shouldn't use null vector, but I'm a little bit no. I didn't try to consider type 2, but now I'm thinking try to extend our definition to type 2 or something other.
Yeah, but that sounds interesting.
Yeah. So if you have some idea. So even for null vector, we can define space like hypersurface, and maybe we can define some charge. Actually, gravitational collapse example, it's type 2. So
yes, exactly. That's why I was asking this question.
Yeah. That's interesting problem. It's open problem so far.
Okay, thank you.
Yeah, the other questions.
Yeah, okay, so I have a question. It's actually a general question regarding quantum gravity. So I think the message here is that in classical theory, you cannot have a proper conserved definition of conserved energy for gravitational fields.
Yeah.
And so, but if you go to quantum theories, and I think if you believe that in quantum theories, one of the most important guiding principle is the conservation unitarity. Conservation probability. Then how, in your opinion, what's your opinion about how to reconcile this kind of fundamental contradiction between classical theory? I mean, if you want to promote to quantum gravity.
Yeah, but I'm not so familiar with the quantum gravity. But problem is, first of all, the Hamiltonian is 0 in the quantum gravity, so it's very difficult. I have no idea.
I see. Can you elaborate more on your final message about like why do you put a question mark on whether we really have to quantize gravitational fields?
Problem is gravity is so special and in this aspect. So usually quantum physics usually based on energy quanta or something. So
right.
Therefore, it's not. I'm not so sure, but my feeling is it may not be necessary to quantize gravity because it's so special.
Okay.
But I might be wrong.
Thank you.
Are there other questions? If not, I suggest we end the official part here. Thank you very much again for the nice talk.
Thank you for
Stop the recording.